In this video, we'll be talking about force analysis and starting with free body diagrams. This is an important topic in robotics. Has to do with things like stability and traction and torque requirements, transmissions, motors, things like that. We're going to kind of go through this material fairly quickly. We'll be talking about we'll just do some free body diagrams, and we'll talk about friction, equations of equilibrium. And one of the things about free body diagrams that every free body diagram should have essential geometry, so that dimensions, so you can figure out where forces are being applied and so on. So essential geometry. And you want to label all the external forces and moments. Forces and moments. And you also want to indicate the coordinate system that you're using. Okay, and the equations of equilibrium will represent a math model of the free body diagram. Okay. So our first example will be, say we have this robot. It's trying to carry this weight up a ramp, and we want to determine how much weight we can carry without the robot tipping over. And also we'll also need to be able to calculate the minimum coefficient of friction for this ramp so that the wheels don't slip. And so in other words, there's actually three reasons you wouldn't be able to get up this ramp. One is the weight's too heavy, so the robot tips. Another is that the coefficient of friction isn't large enough, so the wheels slip. And then the third thing would be if you have a transmission that can't provide adequate torque to be able to turn the wheels to move up the ramp. So you have on the Canvas site, there's a handout that goes with this slide set. So it's Force Analysis 1. I think it just says handout. So it'd be a good idea to print that out. Hopefully you have a printer. And so you might want to just stop the video for a minute and print that out so that you can take some notes, and you'll be making some calculations as well. So the robot here, it's a four-wheel drive robot, okay, and it has it weighs 10 pounds and has a center of gravity 0.5 feet above the ground, and the length of the arm itself is 1.5 feet. And we want to know what's the maximum load before it tips. So in other words, we'll just assume for now that we have a transmission that's adequate, to drive the wheels, and we have a large enough coefficient of friction so the wheels don't slip. But we want to know what's the maximum load before the robot tips. And we'll construct a free body diagram, first of all, of the entire robot. So one of the things about constructing free body diagrams is you want to clearly define the system that you're analyzing. So for instance, if we wanted to, let me just put this on. If we wanted to analyze, how much torque or what kind of transmission we need to lift the arm, to move the arm, then we would probably just do a free body diagram of the arm and the weight. But for this particular problem, we're going to consider the whole thing here, the arm, the weight, the robot, all as one system. And remember that in a free body diagram, you only put in the external forces. You don't put, so for instance, there's a torque from the transmission trying to turn these wheels. We're not going to put that in. That's internal. Or there's a torque here to try and move this or hold this arm in place. That's internal, because we're treating the entire system, the entire robot with the weight as a single system. Okay, so we want to go ahead and draw our free body diagram here. And so first of all, let's see, my pen stopped. So when I put in a force, I'm going to put this line across the tabs here from the arrow. And when it's a dimension, I won't put that, just to make it easy to distinguish between whether you have something that's just an arrow from a dimension or an arrow from a force. So we'll call this load L, and then we have the weight of the robot. So put this in here. I'll just call that W for now. And in terms of the other forces, we have, and again, I'm going to go across the arrow there. So we have these two normal forces. So this is the rear wheel, so I'll call that N sub R, and I'll call this one N sub F. And then we have, it's a four-wheel drive robot, so we also have some frictional force. Okay, some frictional force. And we'll label this front one, we'll call that F sub F because it's a frictional force. And then I'll add another capital F because it's on the front wheel. And this one over here will also be F sub F, and it's on the rear wheel. Okay, so we also need to put some dimensions in here. So let's see, so from the axle right here, this distance to the center of mass is a half a foot. And again, the dimensions, I won't close the arrow. And then this dimension out to the arm here is 1.5 feet. And then we were also told that this is a half a foot off the ground here. Okay. Okay, so this is 1 foot right here. And let's see, what else do we need? The incline we said was 30 degrees. Okay, and I'm just going to put here that the weight is equal to 10 pounds force. Okay, remember that weight is a force. Mass is not the same thing as weight, right? An object that has a certain mass weighs a certain amount on the surface of the Earth. It weighs a different amount on Mars or on the Moon. So the mass is an intrinsic property. The weight depends on the surroundings, and it's a force. Okay, so let's see if we have everything now. We want to make sure we have all the external forces. So we have the weight over here of the load, we'll just call that L. We have the weight of the robot. We have the normal forces on the wheels, and we have the tangential forces due to friction on the two wheels. And so let's see, so all this other stuff like the torque that's being applied to the axle, that's an internal force. The torque that's being applied on this arm to hold that in place, that's an internal force. So the last thing we need to put down here, remember, is we need to define the reference frame. So let's define the reference frame so that, oops, so the X direction, and I'm not sure what's wrong with this pen. The X direction is up the plane, and the Y direction is perpendicular to the plane. My pen seems to be acting up here. Okay. All right. So from the free body diagram now, we want to determine the equations of equilibrium. But before we do that, let's go back to this question right here. How many unknowns are there? All right. So if we look at the free body diagram, we have the load L, and we have the two frictional forces. We don't know what they are. And we have these two normal forces. So there's 5 altogether, right? 5 unknowns. Okay, and so the problem is, from our equations of equilibrium for a two-dimensional problem, we have three equations. So we have three equations and five unknowns. And we know just from algebra that we need to have the same number of independent equations as we do unknowns in order to be able to solve for all the unknowns. Okay, so the question is, well, how can we reduce the number of unknowns in this problem? So if we look at the problem statement carefully, right, where we want to know the load when it's just about to tip. All right, we would like to know the maximum load before it tips. So if we look again at our free body diagram, well, when this is just about to tip, what is the value of the forces on this rear wheel, right? If it's just about to tip, then this normal force goes to zero. And if this force, the normal force between the plane and the robot goes to zero, then there's no frictional force there either. So that gets rid of N sub R and F sub F sub R. So that leaves us with L, F sub F, and N sub F. Okay, so let's write our equations of equilibrium here. So we have, actually, I'm going to ask you, why don't you pause the video just for a minute here, and on your paper, see if you can write out the equations of equilibrium. Okay, so remember that you have the sum of the forces in the x, sum of the forces in the y, and some of the moments about any point. They all have to be zero. So actually, I'll just get you started a little bit here. So we have sum of the forces in the x direction equals zero. Sum of the forces in the y direction equals zero if this is an equilibrium, right? And sum of the moments about any point equals zero. And this is actually about the z-axis, right? We have the xy axis in the plane of the paper, and then the z-axis is coming out straight perpendicular towards us, right? So it's the moment about the z-axis, and just to make this a little bit easier, I'm going to say use this front wheel. So let me go back to here, right? In other words, let's sum moments about this point right here. I'm going to call that point F, right? So this point on the bottom of the wheel here. Now, why would we do that? Well, we could sum moments about any point, right? But the reason, usually you want to pick a point where there's unknowns. In other words, at this point F, these two unknowns, F sub F and N sub F, pass right through the point. So they don't create any twisting about that point because there's no moment arm, right? In other words, you have to have a moment arm in order to get a torque or a moment. So if we pick this point, then F sub F and N sub F won't be in the moment equation. The only unknown that will be in the equation will be L, and we'll be able to solve directly for L. That just makes the algebra a little bit easier. We could pick any other point. It doesn't even have to be on the robot. I mean, it could be 10 feet away from the robot. As long as we sum the moments about, consistently about that point, they have to add up to zero. Okay, so anyway, some moments about that point, and take a minute and pause the video and see if we can, how well you can do writing out those equations, and then we'll pick up again in just a minute. Okay, so hopefully you have equations that look something like this. We have some of the forces in the x direction, and so here's our x direction, and let's see. Right, so our x direction is this way. So you can see that we have F sub E is positive going to the right, and then we have a component L times sine of 30 degrees, and then we also have a component of the weight also times sine of 30 degrees. So, right, so that's where these things come from. And then we have the components in the y direction, and same thing here. We have it's about to tip, so again, these two are 0. So we have our n sub f up. We have y cosine of 30 down, so that's minus, and then we have L cosine of 30 down, right? So that's where we have minus the weight 10 times cosine 30 plus L times 10 times cosine 30. And then we also have some of the moments about the front. So notice all these components here. If what we're looking at here is we're summing moments about this point. So let's look at the L first. So the L component that's down in this direction, that's L cosine 30, right? That's creating a clockwise moment about this point, okay? And the distance to its line of action is going to be 1.5 minus a half, right? Because where this connects, it's right in the middle. So the distance from here out to its line of action is 1, okay? And then we have L times sine of 30, which is in this direction. That has a moment arm of a 1/2 inch. So if we look at our equations here, so this is, right, we had minus L cosine 30 times 1, then we had plus L sine 30 times 0.5. And then these other two are the weight, and they're both positive, right? So we go back. So in other words, the weight, its component in this direction is W cosine theta. It has a moment arm of 0.5 about this point, and then the horizontal, the x direction one here, which is going in this direction, that's W times sine of theta. That also has a moment arm of a 1/2. Okay, so we have the three equations now, and as I said, notice that this moment equation, the only unknown in it is L. So we can just go ahead and solve for L. Okay, and from the other equations, we could solve for n sub f and f sub f. Right? Once you have once you solve for L, you can put that in this equation, solve for n sub f, and once again you have L, you can put in here and solve for f sub f. Okay, so let's look at solving the load. That's no problem. What about the minimum coefficient of friction? So the coefficient of friction, right? The relationship between the normal force, right? So in other words, we had f sub f sub f. The relationship between f sub f and the normal force n sub f, if it's just about the slip, will be just this constant right here. So, and this is called the coefficient of friction. Okay, so the frictional force when the object is just about to slip is equal to the normal force between the two surfaces times the coefficient of friction. Now, if the object isn't just about to slip, then that's not true, right? So this equation is only true when it's just about to slip, or this would be a static coefficient of friction right here. We'd also have a kinetic coefficient of friction. We'll talk a little bit more about that later. But anyways, if you look at the equations that you have here, you can solve for f sub f, and you can solve for n sub f. And so now you can determine the minimum coefficient of friction. So what I'd like you to do is to go ahead and make those calculations, and then there's a quiz. So you can go ahead and put your answers into the quiz, and you'll have three chances to put those in, and then you'll be able to see the slides with the rest of the calculations worked out.